Xarray and Dask part 2, which is focusing on translation. So hopefully I've spent most of the last session explaining to you why we should care about fast code and why that's worth thinking about, and then looking at what's happening under the hood for Xarray and Dask. And that I stopped just before I got to the kind of key point, which is, given all these reasons to use Xarray and Dask and a bit of an understanding of how they work, how do you actually put that into practice? So how do you take this analysis code or this scientific analysis that you want to run and write Xarray code that then does that? I'm going to switch back to a PowerPoint here. There'll be space for more questions at the end. So we spent just then and last week looking at what fast and good code means. And then Xarray and Dask can generally run faster than Python code, so you're better off passing things back through to Xarray and Dask in as big a piece as possible. And when Dask is working and you have something running in the scheduler looking at different chunks, it kind of works by breaking it in different pieces and then doing some maths on individual pieces and then bringing everything together at the end. So if you're summing across a large array that has chunks, Dask might sum across each of those chunks individually and then merge them together. And if you've been taught to code in C or MATLAB or whatever other pre-Python language going, then switching to do stuff synchronously with Xarray and Dask is really weird. It really does your head in, and it really took me a while to get my head around it. So you kind of switch across this new thing, and it's a cliff to climb, it's a mountain to climb. And then after a while, people get the hang of it. And I was thinking back over what I do, and I've tried to summarize that for you in the next few slides, so that instead of people coming into this field and having a mountain to climb, we can have a set of stairs where it's easier to learn these new bits and kind of get going with science using Xarray and Dask. And so everything I've shown has been an average or a sum from the stuff I showed just then and all of the last session. But there's a few different tools available, and you can almost always rewrite any kind of scientific analysis into these pieces. So the stuff you can do includes any kind of maths. So you can do multiplication, addition between arrays. You can take the log of something, take a cumulative sum along a dimension, and that's kind of stuff that changes your array in place, just does something to the numbers. So in this example here, you can take the square root of every individual element. You can do dimension reduction, and I've split this into by maths and by picking one. So if I can work out how to draw on my slides, dimension reduction, you might take standard deviation of each of these rows, put that in this thing at the end. Alternatively, you could reduce your dimension by maybe picking one. So you might say that's the smallest, that's the smallest, that's the smallest, or you could take the maximum, or you could select something along that dimension. You can move stuff around. So shift moves the entire block sideways a certain amount, or coarsen breaks things into smaller pieces that you can then average or take minimums or maximums on. And the last section I've got here, if I can work out how to get back. Is you can grab individual pieces. So you can use .where to find parts of an array where some condition is true and replace everything else with nans or with some other fill value. Or you could use group by to do something like pick out every single January or put things into different piles for different months. And that's usually useful for thinking in climatology. And there's this whole list available online, but I think that set of 5 sums up almost all the options available to you. So the question is then not, oh, how do I generically rewrite my function as an Xarray thing, but can you break your problem into some set of these pieces? And so I've got 4 examples here, none of which are technically oceanography. They're all climate science coupled models, but the ideas should still translate. And I would strongly encourage suggestions or questions from people who haven't done the specific analysis I'm talking about. If you're doing the same thing to the entire data set, like you wanted to multiply everything by 2, or you wanted to multiply 2 arrays together, it wouldn't really matter what shape the chunks were, just they were a reasonable size.
And
so my first example here is calculating the NO3-4 index, which is the average sea surface temperature within a particular box. And so you just want to average sea surface temperature in that box. And we can rewrite that as calculating average sea surface temperature within the NO3-4 region for every time. And then I'm just color coding that as 2 steps that you want to select stuff within the NO3-4 region and average it. So that first step can be done using either cell, so picking out latitudes within that particular slide, like latitude and longitude slices, or if you're sitting on a funny ocean grid and you don't know exactly what latitudes and longitudes are because it's the one where the poles moved over the Greenland or somewhere, you could use where. So subsetting data for just where latitude is less than -5. That should be a greater than, sorry, greater than -5 and less than +5. Clearly I hadn't had enough caffeine when I made this slide. So just ignore that bit and that bit. And the general idea is that you can find sea surface temperature where one particular condition is true, and then you can average that. And so those are 2 simple Xarray steps, but thinking about turning that word explanation if I want to get this average sea surface temperature into some code. Increasing in complexity slightly. This is one from Georgie Falster, looking at rolling weighted averages through time. And so a rolling weighted average can be broken into an equation of it's a rolling sum of weights times data divided by weights. This is pretty much a weighted average. If you want to do a weighted average in another sense, you could do the same thing. And so if we break that into 3 steps, we want a rolling sum of weights times data. So weights times data is just doing some maths together. And then you can use dot rolling to break that into pieces. Say we're looking at the time dimension, and then sum that rolling construct. And you can do the same thing for the bottom, where you can take the weights and roll them through time and then sum it, and then dividing the 2 by each other is just using that little divide symbol. So, and this is one that Xarray doesn't have an explicit function for, that it's not going to give you a rolling weighted average function. But if you break it down into its constituent pieces, all of those pieces are doable. Increasing in complexity again. Is 20-degree isotherm something that people in the ocean community are generally familiar with? Give me a thumbs up or a thumbs down. So just trying to calculate the depth of 20 degrees, which if you look at it, you can kind of draw it on, or if you were using a for loop, you could step through, is this depth above it or now? What about now? But we're trying to do it with Xarray in a parallelized sense. So 20-degree isotherm can be rephrased as the depth that is 20 degrees. And if we're going to take that another step further, it's pretty much the deepest depth warmer than 20 degrees. So if we have a box of temperatures and we have, I've colored in red everything warmer than 20 degrees and blue everything colder than 20 degrees, you could say 20-degree isotherm is, sorry, I'm drawing with a touchpad, the deepest depth that's still warmer. And so you can start by calculating which depths are warmer, and then if you use where, you can scribble out everything colder than that. So we'd have a bunch of depths and then some nans below that. But once you've gotten rid of all those deep depths, or like all the cold depths, you can find the deepest depth using something like argmax. So finding the argument of the maximum depth that hasn't been replaced by a nan in the where. or you could use IDX max, which would give you the depth itself as opposed to the index of that depth. That's the deepest bit we haven't gotten rid of in this first step. Have I lost people yet? So if this was temperature and I put temperature.imax depth, it's just going to give me the surface basically every time. Yeah. Still following, I'm going to add another step of complexity here. And this is analog forecast, which I think many of you have seen me talk about, but possibly not the technicalities for how these are calculated. And the broad aim here is to find months in model output that look similar to some target months so that you can use these to forecast. Ooh. And that's a very broad statement, but as with the other examples, you can break that down into two sections, that you find some kind of similarity to your target months, and then you want the ones that are most similar. So in my case, I was using mean squared error to calculate similarity. And so the first line of finding these analogs is calculating mean squared error for all of these. So looking at the difference between the sea surface temperature and the target sea surface temperature, and then square that and find the mean. And then having done that, I now have a single number for all of my potential months that could be used as analogs. And you can either use something like IDX max to pick out the one that matches the most, or I found a bit of a shortcut for finding several of them, where if you then sort that similarity, then you can pick out the first 10 in the sort, like after you've sorted it, and that gives you the 10 months that match most closely. So if you write down what you're looking for and you break that into small pieces, almost any scientific analysis can come back to these simple functions that are implemented already in Xarray. And then there's a few more that don't. So if you've tried and for some reason it just doesn't work, or there's this really nice SciPy function that you want to use that just doesn't work with Xarray, you can throw everything in a bucket and stick a label on it and say it's an Xarray function. And the way you do this is using xr.applyufunc, and it doesn't really have any nice explanation. You just make a function and then you follow the instructions on the COSIMA recipes tutorial line by line, which I could go through now, but they're explained there. So if this is something you want to do, have a look there. And then that turns your bucket of messy Python function into something that Xarray can work with. And that can be really useful for getting multiple cores, and that Xarray distributed functionality to work with something that's more complex that can't actually be broken down into smaller pieces. Trying to calculate the significance of a correlation or a trend, you can do it yourself. It's much faster to use SciPy. SciPy refuses to work with Xarray. SciPy only wants a NumPy array. So you can have a SciPy function and then wrap it up with applyufunc and hand it across. And then Xarray can apply that SciPy function to each grid cell, but using multiple workers instead of waiting for it to run in serial. I think Ashley did something funny about doing a Fourier breakdown of different modes at different depths. And that was also something he couldn't natively do in Xarray, but he didn't want to wait ages for this decomposition into different waves to run like in one direction. So he broke it down something like this. Xarray does not decide the way to slice things up, you have to. This, there's another line up above here that I've cut off, but you generally be really careful with your chunks before you put any information into that function. And then these lines at the bottom say, yes, I'm okay with it being vectorized, but the function can't do it on itself. And so it does the same thing one by one to the chunks that you've pre-established. And these bits here, so this is a SciPy function. It says SciPy can handle the one dimension of time. Everything else, I want you to break up into different pieces. The general broad summary is if you have something that doesn't really work in Xarray and you've tried and you really can't get it to work, you make a bucket and you throw all of the messy function into the bucket. And this bucket is called xr.applyufunc, and the tutorial is here.
Like for SciPy.
Like for SciPy. I have to offer here is there's not enough documentation on this kind of stuff to train ChatGPT, and it tends to spout bullshit on Xarray and Dask. That was what I arrived at after some experimentation. You have to have the set of specific keywords for it to work. It seems like this function is written to do a few different things, but not all combinations of keywords. So if you have Dask equals parallelized, I think you also need vectorized equals true, and you need to set up nicely, and you need to have the input-output coordinates.
Thanks.
I was just going to add that ApplyUfunc, I think, is a tool that everyone would find very handy if they knew how to use it. So I don't think it should just be a last resort, but it is complicated. I think that's kind of related to the questions that have come up. So like the best practice would be that your function that you provide can actually handle the Dask arrays themselves, and then you can use Dask aloud.
Okay.
By doing vectorize equals true, you're actually wrapping it with a numpy vectorized function, which is essentially just a for loop. So it's not the fastest you could possibly achieve. It's an easy way to like have the functionality that you require. But if you're really chasing speed, then there are like more complicated things you can do. But maybe we should do like a session just on ApplyUfunc.
I'd definitely be open to expanding the tutorial for different things that you could do with it.
It's really very powerful, and it's kind of like an essential tool if you're wanting to do complex or really custom stuff with on Xarray objects. In a way that actually performs. That's all.
I'm going to skip forwards to the last 3 or 4 slides, and then I will be open to all questions. So I guess I've shown this slide a lot in the last 20 minutes, and that's what I would hope that I've covered in this session, the last session. But really what I hope is I've shown you a slightly different way of thinking about code and how you use Xarray and Dask. And that different way of thinking can propel you forwards into the future and let you do more interesting, fun science. So good luck with these troublesome libraries. And I am open to questions, and I am really appreciate descriptions of what type of further resources and further support you'd appreciate to use Xarray and Dask better. Sometimes developing a dummy data set where you know exactly what's going on and it's only 5 by 3, and then throwing the function at it lets you work out what's going on. But it would be ideal if we didn't have to try and reverse engineer functions like that.
I think Charles, I'll probably say the same thing as you. Charles has got a tool to do exactly that. So the first option is just to open the data with the default chunking, which will use the netcdf chunks, and then you can look at what you get back. It's kind of a bit horrible and circular.
I'm going to jump on that and say open the data with a single file to check what you get, because if you use MF dataset, it does.
Yeah, you only need to check one, I suppose. Well, hopefully, unless the chunking changes between the files. But Charles is working on I think he already has a tool that's bundled in with the intake catalog to just query a file and see what the chunks are, so you can make a sensible choice about how to specify the Dask chunks. Yeah, I agree with everything everyone just said, but the reason I had my hand up was just because I just wanted to check that people had come across in the Xarray documentation, there's a tutorial section and a gallery section, and both of those have pretty detailed examples on some of the stuff we talked about. Like ApplyUfunc is discussed in quite a lot of detail with examples on how to use it and how not to use it.